So today we are going to talk about a basic introduction to filters, and then we are going to specifically cover first order filters today. Um, what I've literally never had this try to do text. Now I have to figure out how to make my pen be a pen. Jesus Christ. Maybe that thing. Is it off now? Okay. Thank goodness. So here in circuits 2, we are only going to concern ourselves with extremely simple first and second order filters. I'm mainly introducing this material to you now so that when we get to higher order filters and topologies like Chebyshev filters, Butterworth filters, potentially elliptical filters and Bessel filters and all of that kind of stuff in circuits 3, that you have some kind of understanding of where this is coming from. Okay. So in essence, a filter circuit is doing exactly what you would expect any filter to do. It is filtering out unwanted something. In the case of these electrical circuits, it is filtering out unwanted frequencies from our signal, okay? So there are 4 very basic types of filters that we might have, okay? And I'm going to talk our way through the 4 of them, but I want to introduce you to something while we're doing that. And so this is going to be a frequency response curve for these filters. So the first filter that I'm going to put over here on the left is going to look something like this. And I'm going to choose to represent it in this particular way. So my vertical axis is going to be the magnitude of the transfer function of my filter, okay? So h of j omega, or h as a function of j omega, is what's going to be the transfer function of my filter. And when we start looking at actual circuits, that'll maybe make a little bit more sense. We are only concerned with the magnitude of this quantity, okay? So phase is going to come into play, but for what we're looking at right now, we're only dealing with the magnitude. And then over here on this particular axis, we are going to have omega measured in radians per second, okay? So for these idealized filters, they are going to have what is commonly referred to as a brick wall response. And you'll see what I mean by that here in a moment. So let's say for this particular filter that it is passing signals up to some certain point, and then it immediately starts rejecting signals like so. Okay. So this frequency right here, where our filter's output changes from passing signals, meaning our output is high, to rejecting signals, meaning our output is essentially low, is what is typically referred to as the corner frequency or the cutoff frequency. So I'm going to call that omega C, okay? Doesn't matter if we consider it corner or cutoff, it's the same letter down there, okay? So everything to the left of omega C is what we would consider to be the pass band of this filter, and everything to the right would be the stop band for this filter, okay? Now, this is an idealized version of what is commonly referred to as a low pass filter. So I'm going to write over here to the left, LPF, okay, standing for low pass filter, okay. So we call it a low pass filter because all of the signals below the corner frequency or the cutoff frequency are passed, and all of the signals having a higher frequency than our corner or cutoff frequency are rejected or attenuated. Now, a real low pass filter will not have a response that looks like this, okay? Real filters might look something like this over here to the right, okay? And I'm going to make a minor change for some things as well over here. So I'm going to draw this graph as if it were the result of, let's say, an LT Spice simulation or something like that, okay? So in LT Spice, typically we would see that our x-axis would actually be linear frequency instead of angular frequency. And our vertical axis, it'll still be the magnitude of our transfer function, but instead of it being the explicit magnitude, it's actually going to be in a decibel scale. So this would be 20 log of the magnitude of h as a function of frequency now. Okay. So for a real practical low pass filter, instead of having this very exaggerated transition where we instantaneously phase from the pass band into the stop band, what we're going to see actually is a much more gradual transition. So something akin to this. And the slope of this line here in the stop band is dependent on the order of the filter, okay? So a first order filter is going to have a slope of -20, what are called decibels per decade. A second order filter is going to have a slope of -40 decibels per decade. A third order filter is going to be -60 decibels per decade, et cetera, et cetera, et cetera. We're going to get into the nitty gritty of why they behave that way once we start analyzing circuits in the Laplace domain in circuits 3, okay? But essentially, the higher the order of the filter is, the steeper that transition from the pass band into the stop band is, okay? Now, let's officially define where our corner frequency is for something like this. So I'm going to say that this point right here represents where my corner frequency FC is going to be, okay? Now, this is very commonly also referred to as F minus 3 decibels, or your minus 3 dB cutoff frequency. The reason for that is that the maximum value of the output of our filter, which is going to be up here. So let me just call this max. Well, down here, this is literally just the maximum value minus 3 decibels. Okay, so it's just 3 dB lower than the maximum. So the reason why that minus 3 dB frequency is so important is because that is actually the frequency at which half of our incident power has been attenuated, okay? So if we looked at, I'm trying to make this too damn busy, but I don't really have a choice here, okay? So essentially, this would be either the maximum amplitude of the voltage divided by the square root of 2, okay, which corresponds to the power over a factor of just 2. So this is why it's a half power frequency. And because power is related to voltage squared, when we square Vmax over root 2, that's going to give us effectively a representation of the power divided by a factor of 2. Okay. So the corner frequency in a practical filter is just the frequency at which the power of the output signal has fallen to exactly 1/2 of its maximum value. Okay. And we're going to use that as a figure of merit once we start looking at some circuits in a little bit. Okay. So I think I have most of the background covered here in this graph, introducing things for low-pass filters. So now let's look at a couple of other filters that we might see. Okay. So down here, we're going to look at a high-pass filter. And effectively, it is going to be the exact opposite of a low-pass filter. So we're going to see that our signal is attenuated for low frequencies, and then it will be passed for high frequencies. Right? So this is a high-pass filter. Here is our stop band. Here is our pass band. And then here is our corner or cutoff frequency. For a real high-pass filter, we are essentially going to have the same thing as our low-pass filter, except that it is flipped around. So we might have something like this, where once again, here is our max. So wherever we have our maximum and we take 3 dB away from that is where we're going to wind up having our corner frequency or our minus 3 dB cutoff frequency. And once again, that slope now, even though it's directed down and to the left, the height of that slope is still going to be related to our filter's order. So as we're dealing with increasing frequency, now we would see that our filter's output increases by a factor of 20 decibels per decade per order of our filter. Okay. So these two basic filters, our low-pass filter and our high-pass filter, can be implemented with a circuit as low as a first-order filter, meaning only an RC circuit or only an RL circuit. For the next two that we're going to talk about, which is going to be our band pass and our band stop, they require us to have at a minimum a second-order filter. Ka, what's up? So that's a fantastic question. So why do we need to filter frequencies? Okay. So filters are used in a ton of different applications. You guys don't need to write this stuff down. I'm actually going to very, very basically go over a topic that's going to be covered early on in your electronics class real here, because this is one of the most obvious places that you would see a filter circuit, okay? So don't write this down because this is completely related to a different class that you guys are going to get in your junior year. But for a very basic filter circuit, so let's say, Jesus, and this is also tangentially related to something that you're going to cover in circuits 3 as well. So I'm going to just break your brains and talk about not only diodes, but also transformers. So I pre-apologize. So let's say this is the primary coil of a transformer, an ideal transformer. So this voltage right here is some sinusoidal, I'm showing, let me call this V1. So this is some sinusoidally varying voltage drop across the primary coil of this transformer. I'm going to call it an ideal transformer. It doesn't make any difference to you guys because you probably have never seen transformers before from a circuit analysis perspective. Here is our secondary coil of our transformer. So I'm going to call this guy right here V2 of T. If this has N1 turns and this has N2 turns, then for what it's worth, V2 of T is just going to be N1 over N2 times V1 of T. So let's assume that this is a step-down transformer, so we're making that output voltage on the secondary side of our transformer smaller. Well, what we might do with that reduced or scaled down sinusoidal voltage is we might run it through a simple circuit, okay? So if I were to put a diode right here in series with a resistor, and then I take the voltage drop across this resistor, let's going to call this V out 1, my signals would look something like this, okay? So this is a function of time. So let's say that this guy in blue is V2 of T. Something like that, okay? Well, I'm going to do V out 1 here in purple, okay? So what our diode is going to wind up doing in this circuit is that it's going to essentially allow only the positive half cycles of our waveform to actually go through, and it's going to reject the negative half cycles because a diode is essentially a unidirectional valve or a one-directional valve for current to flow through. So realistically, our output voltage would look something like this, where the value of this voltage is a little bit less than our input voltage because it requires a little bit of voltage for our diode to turn on. That's typically on the ballpark of 0.7 volts for a silicon diode, around 0.3 volts for a germanium diode, and I think it's around 1.1 volts for a gallium arsenide diode. But anyway, so essentially, we are going to only pass through half of our cycle, the positive half cycle, and it's going to be reduced by a little bit. Now, that is some dirty looking electricity, okay? It could be useful for what it's worth. How many of you guys, actually, how many of you guys as grandparents had like a touch lamp or anything like that? So a touch lamp works on a situation like this, okay? You pass the output through. This is called a half-wave rectifier circuit. This diode just directly in series with this resistor, and roughly only half of the power makes it to the light bulb, and so it's dimmer, okay? But if we wanted to use this half-wave rectifier to generate essentially DC power, okay, because that's what a rectifier's real job is, we need to add some filtering in the form of a capacitor, okay? So we would just put a capacitor here, like so. And what that's going to do is, depending on the size of the capacitor, it's going to provide some form of energy storage. And so now, instead of our voltage falling off like that, it's going to gradually decay like so. And the larger that capacitor is, the more filtering it provides. And so we can eventually get a capacitor large enough to where this ripple voltage, so the peak minus how much it's allowed to fall down to, becomes smaller and smaller and smaller until this signal eventually looks like DC, okay? So that is us effectively filtering out any high frequency response of our input signal and making it look only like DC, okay? Now, this is an application with regards to power electronics, but filters are used all over communication systems and all of that kind of stuff. Our phones have tens, if not hundreds, of filters built in to handle a lot of the signal processing that we need. Think about it in this way, okay? The cellular telephony band ranges from, if I'm remembering correctly, and forgive me if I'm off here, but I think it's around 1.8 gigahertz to 2.2 gigahertz or something like that, okay? So that's the total available spectrum, okay? Well, there are hundreds, if not millions of, hundreds, if not thousands, if not millions of users that are using their cell phones in any given region connected to a single cell phone tower. So in order for me to only pick up my call and not everyone else's call, we have to have a filter in our phone that has an incredible level of what's called selectivity, so that it only sends us our signal, but attenuates everyone else's, okay? So that's another very basic application of filter. It's the same thing that's done at how we can tune into one particular radio station and not hear too much, crosstalk with other signals or other radio stations and all that kind of stuff, but on a much, much narrower scale. Okay. Did that sufficiently answer your question? Okay. So let's go back to the actual topic at hand. So we've got these basic first order filters, or filters that can be implemented with a first order circuit or higher. Now let's talk about those two that require, at a minimum, a second order filter. So the first of these is going to be a band pass filter, okay? So BPF, once again, here is our transfer function. Here is omega. And then a band pass filter, we are going to see a stop band and then a pass band and then another stop band, so that only frequencies within this range get passed, and anything either lower than the low frequency cutoff or higher than the high frequency cutoff gets rejected, okay? So this center frequency is going to be omega naught. And that is the resonant frequency for this particular circuit. Then over here, we're going to have what I'm just going to call omega low, and it represents one of two different cutoff frequencies. And over here, we're going to have omega high, right? So here's a stop band. Here's another stop band. And in the middle here, we have our pass band. For a real band pass filter, it's going to look something like this. Where, once again, if this represents our maximum value, then 3 dBs less than our maximum value is where we are going to hit our cutoff frequencies. So I'm just going to extend this dashed line all the way across like so. And so this particular frequency right here is our low minus 3 dB frequency. And this guy over here is our high minus 3 dB frequency. The middle is going to be F naught, which is just our linear resonant frequency for this circuit. Okay. For what it's worth, this distance between omega low and omega high, and similarly, this distance between F low and F high is what's commonly referred to as our filter's bandwidth. Okay. Our last one that we're going to introduce is going to be a band stop filter, also commonly referred to as a notch filter. So in our band stop filter, we're going to see that at low frequencies, our signal is passed through. At intermediate frequencies, it is attenuated. And at high frequencies, it started to pass again. Okay. So we have a pass band over here on the left, a pass band over here on the right, and a stop band here in the middle. Well, the middle of the stop band is the resonant frequency for this circuit. And then this is our omega low cutoff frequency and our omega high cutoff frequency. And for our practical implementation, we'll have something like this. Whoa, what's going on down there isn't particularly important, but anyway. So the middle here is F naught. And then if this is our maximum value, here's our minus 3 dB frequency. And so here is F low, and here is F high. So bandpass filters are obviously used whenever we want to just pick up some specific frequency band of interest. So the filters that are in our cell phones are bandpass filters. The filters that are making sure that we're picking up the Wi-Fi signals that we're interested in and all of that kind of stuff are also band pass filters. Band stop filters just reject frequencies over a particular range that we consider to be noisy and don't want to pick up. So there's probably some band stop filters in our phone as well. I can't think of any specific applications of a band stop filter off just the top of my head, but they are indeed very widely used in communication systems. Okay. All right. So these are the four basic types of filters that we're going to see, just low pass, high pass, band pass, and band stop. Now let's talk about how we can implement some of these filter circuits using actual components, okay? So I'm going to start with a simple low pass filter, okay? So I'm going to call this I don't know why it's in green. First order low pass filter. And I'm going to call this version 1 because there's two different ways that we could implement this circuit. Depending on time, we probably won't go through the full derivation for all of these. I'll just show you the topology and tell you briefly how it works, okay? But for this first one, let's pay attention to some details, okay? So I'm going to start essentially with a voltage source, okay? So we're only going to be concerning ourselves with voltage signal filtering for today's stuff, okay? And so this is going to be my input signal explicitly monitored as a function of omega, okay? So what I tend to do in all of my analysis is I say that this input signal is really just a phasor of 1 angle 0 degrees volts, but it has that same phasor for all frequencies. So it doesn't matter if I'm at DC or it doesn't matter if I'm at a frequency of, let's say, 679,522 radians per second, whatever. It's always just 1 angle 0, okay? And you'll see why in a moment. So I would apply that particular input signal across the input side of my filter. So in this case, our filter is literally just going to be some resistance R in series with some capacitance C, okay? Since I'm working with a frequency domain circuit, I'm going to represent this capacitor by its impedance of 1 over j omega C. And then over here on the right-hand side of my network is going to be the output terminals of my filter, which could then be connected to some sort of load or something like that if we were so inclined, okay? So this is an incredibly basic filter circuit, but it is actually one that you see used very frequently, particularly in power supplies and stuff like that, okay? So I'm going to define the transfer function of this filter, h of j omega, and this is a complex number, okay, is simply going to be the ratio of our output voltage as a function of frequency divided by our input voltage as a function of frequency, okay? So transfer function is literally just playing the role of voltage gain in this AC system. Output voltage over input voltage, okay? So over here on the left, I'm going to try to figure out what my transfer function is. So does anybody have any thoughts on how we might approach this? Perfect. That is exactly what I wanted to hear. So this circuit is literally just a voltage divider. It's just an AC voltage divider, right? So our output signal is just the voltage drop across the capacitor. So we would have V out is equal to 1 over j omega c plus, or excuse me, over R plus 1 over j omega c. Well, if I divide both sides by my input signal, which is just 1 angle 0, essentially my transfer function for this guy is going to be 1 over j omega c divided by R plus 1 over j omega c. For what it's worth, for these voltage filters, we're always just going to use voltage division for these simple ones. It's not until we get into higher order filters and other topologies that we have to do anything other than treat it like a voltage divider and see what shakes out, okay? So I personally think this is ugly. And so I'm going to just multiply through by a factor of j omega c over j omega c so that I don't have fractions inside of fractions and stuff like that. And so in doing so, what I'm going to wind up getting is 1 divided by 1 plus j omega RC. And this is how I would designate my transfer function for this particular circuit in the most simplistic form, okay? Now, we are going to take this and we are going to manipulate it in order to get not only our magnitude response and our phase response, but we're also going to use this to figure out what our cutoff frequencies are and prove that it's a low-pass filter as well, okay? So this is our jumping off point, okay? Literally, take the voltage divider relationship and then make it to where it doesn't have too many fractions, and then go from there, okay? So what I'm going to do first is I'm going to figure out how to split this thing up into both its real part and its imaginary part. So instead of it being a fraction, I want it as effectively just a rectangular form complex number, because I know that the magnitude is just going to be the square root of the real part squared plus the imaginary part squared. And I know that my phase response is just going to be the inverse tangent of the imaginary part over the real part, okay? So literally just the exact relationships that we developed in circuits 1 for dealing with complex numbers, I'm now going to use to describe how this filter actually works, okay? So starting with this relationship, 1 over 1 plus j omega RC. Anybody have any thoughts on how I'm going to break this guy up into its real and imaginary parts? Another way to put this is, how do I get rid of a complex number in the denominator? Multiply by the complex conjugate of the denominator, okay? So I'm going to multiply this guy by a factor of 1 minus j omega RC over 1 minus j omega RC. Okay. So what's the real part of my numerator going to be? 1, because 1 times 1 is equal to 1. So I'm going to have 1 over, now what's my denominator? Well, it's just going to be 1 squared plus omega RC squared, because j times negative j is negative j squared, or positive 1. and my cross terms are going to cancel each other out. That's why I multiplied specifically by the conjugate of the denominator. So I'm going to have 1 plus omega RC squared down here. And then my imaginary part, so I'm going to have a factor of 1 times minus j. So I'm just going to pull that minus j out. And now I'm going to have omega RC divided by that exact same denominator of 1 plus omega RC quantity squared. So this is my transfer function broken down into its real and imaginary parts. Okay, so just a rectangular form complex number. So from here, I can get my magnitude response. So this is where those graphs that we had at the very beginning of class effectively come from. Okay. So the magnitude of this complex number is simply going to be the square root of the real part. So that's going to look like 1 over 1 plus omega RC squared. Square that whole thing. Plus the imaginary part. I'm going to throw away the negative because I'm squaring it, so it's not going to matter. Omega RC over 1 plus omega RC squared. Close that off and square it. And now I'm just going to simplify it, okay? So 1 squared plus omega RC squared is going to look like 1 plus omega RC quantity squared in my numerator. And then my denominator is just going to be 1 plus omega RC squared. And when those denominators multiply by each other, that whole term gets squared. And now I can see that this numerator is the exact same thing as I have in my denominator. So that's going to get rid of that. And that's going to lower that power by 1. And so the result of this is just 1 divided by the square root of 1 plus omega RC quantity squared. So this relationship exactly describes how the magnitude of my filter is going to work. So now let's prove that this is a low-pass filter, okay? So what is the magnitude of this guy when omega is equal to 0? 1, because I'll have 1 over the square root of 1, which is just 1, okay? So that means that at low frequencies, essentially, I'm passing all of my input signal to the output because the ratio of V out to V in is 1, okay? What happens at high frequencies? Okay. So if we consider where omega is equal to infinity, then obviously omega RC quantity squared is going to be much, much larger than 1. So I have what is essentially 1 over the square root of infinity squared, or 1 over infinity, which looks like 0, essentially. So very low frequencies are passed, very high frequencies are rejected. This is indeed a low pass filter, okay? Now let's see if we can't sort out, using this, what our corner frequency is going to be, okay? So let me go back up here, okay? So I said our corner frequency is defined to be where our maximum value of our output voltage is divided by the square root of 2. Well, what do you think the maximum value of this output is going to be? Literally 1, right? Because as omega becomes larger than 0, that makes that denominator larger and larger and larger, which causes that ratio to get smaller and smaller and smaller. So essentially, I'm saying that 1 over the square root of 1 plus omega RC quantity squared needs to equal 1 over the square root of 2. How they get what? Binary numbers? No. So I already have a 1 in the denominator, so I don't need to do any work for that. I have a square root in the denominator, so I don't need to do any work for that. So realistically, that 1 plus omega RC squared needs to look like 2, or to put it in another way, omega RC squared must equal 1, right? Well, if omega RC squared must equal 1, then omega RC must also equal 1. And so what we would find is that our cutoff frequency, omega C in this case, is literally just going to be 1 over RC. Okay. The last thing that I'm interested in is our phase response, okay? So theta as a function of j omega, excuse me, is just the inverse tangent of the imaginary part over the real part. So let me scroll up here really quickly, okay? So we see our imaginary part and our real part right here. I'm taking the ratio of those two things, but notice that they have the same denominator. So those denominators are going to cancel each other out. So I'm not even going to bother writing those down. So realistically, what this is going to be is the inverse tangent of negative omega RC divided by 1. And as it turns out, the inverse tangent of a negative number is the same thing as negative the inverse tangent. And now I just have omega RC like so. Okay. So these are all of our relationships for this low pass filter implemented by using a resistor in series with a capacitor. And I want to note here that we're taking the voltage drop across the capacitor. So I've gone ahead and created a very simple LT Spice circuit. So I have here as V out 1 is literally just the circuit that we did, okay? So if I click on this output voltage, I get a low pass filter. The solid line represents the magnitude response, and the dotted line represents the phase response, okay? So those are both two parts of the same thing, okay? So we can see very easily that at very low frequencies, all of our input signal gets passed to the output. And then as soon as we get to somewhere in this region, we've dropped by approximately -3 dBs, and then we start rolling off and attenuating signals. Let me get rid of this delete thing here. So I want to look at this stuff, okay? So our maximum value, sorry, we come all the way over here to the left, is essentially 0 dBs. It says -180 microdecibels. That's 0 to me. So realistically, my cutoff frequency is just wherever this guy is going to hit -3 dB. So if we grab this guy and just keep going, I'm looking for where it says my magnitude is -3 decibels. So about right here, 160 millihertz. Let me get this thing out of the way. So based on that value of R and C, where do you think the cutoff frequency is supposed to be? Do the math. I feel like 1 over 1 times 1 should be pretty easy to do. So what should our cutoff frequency be? 1. 1 radian per second. This is in linear frequency. What's 1 divided by 2 pi? To put it in linear frequency. You got a calculator in front of you, Nikolai. Like pretty damn close to 0.161 or yeah, 0.161 hertz, right? Yeah. So, I mean, this only has a finite resolution, so I can't really nail exactly where it's supposed to hit. But yeah, this tells us that our resonant frequency or our cutoff frequency for this particular circuit aligns almost exactly with where we would expect it to be. Okay. One thing that I do want to note here. So this is your first time that you've probably ever seen an AC circuit analysis thing. So I want to talk to you about how you could set this up just really quickly. The most important part of this is the source itself, okay? So I had to go into the advanced tabs, and these settings are pretty complicated, so I want to make sure that you can follow. By the way, that's utter sarcasm. Literally, all I did was I went over here to where it said small signal AC analysis, and I put the AC amplitude as 1, and then I literally left everything else blank. So now when I take my output voltage, because my input signal is literally just 1 angle 0, my output voltage is the exact same thing as my transfer function, okay? Another thing that I want to point out in setting up the simulation command, so I went over to this second tab and did an AC analysis. I told it that I wanted to do a decade sweep. I have the number of points per decade as 1 times 10 to the 6. So 1,000,000 points per decade, okay? I have a start frequency of 1 millihertz and a stop frequency of 1 kilohertz. I just want to show you guys what happens if I only use like 1 point per decade. I'm going to get roughly this graph, but it's going to look like utter shit, okay? So if I rerun this simulation, now it's all disjointed and wonky looking because I'm not taking enough data over each individual decade. So the higher you increase that number of points per decade, the more smooth your graph is going to look like. I'm mentioning this to you very specifically because you're going to have a design project related to this, and I'm tired of you guys turning in shit work where you get crazy disjointed looking graphs, and you can fix it simply by including more points per decade so that it looks nice and smooth. So please, for the love of God, do that, okay? So it didn't change the simulation time for me practically at all to go from 1 point per decade to literally 1,000,000 points per decade. So that's probably overkill, but it gives me a very nice looking graph. So that's what I tend to use. For more complex systems, I might lower it down to only 1,000 points per decade, something like that, to increase simulation time. Or excuse me, to decrease simulation time. So one other thing that I want to point out real quick, so now I'm going to go over here and I'm going to click on V out 4, okay? So I want you guys to look at this circuit really quickly, okay? So this is now a filter that is implemented using an inductor in series with a resistor, and we're taking the voltage drop across the resistor. So if I click this node V out 4, it completely overlapped the output of my capacitor-based low-pass filter, okay? So in a first-order circuit, we have 2 different options to implement a low-pass filter. We either have an RC circuit where we take the voltage drop across the capacitor, or we have an RL circuit where we take the voltage drop across the resistor. I'd like to try to very quickly explain to you why things work this way. All of these filters are literally just exploiting the fact that the impedance of the energy storage elements is dependent on the frequency. So when we think about a capacitor, at very low frequencies, a capacitor looks like what? Let's say the lowest of frequencies, DC. What does a capacitor look like at DC? An open circuit, right? 1 over j omega c is going to look like 1 over 0, or an infinitely large impedance, right? An open circuit. At really, really high frequencies, a capacitor actually starts looking at like a short circuit. And so this part of the curve right here is us transitioning between looking like an open circuit to the left and looking like a short circuit to the right, okay? So essentially, when we're taking the voltage drop across a capacitor, we are always going to wind up with a low pass filter response because the capacitor always looks like an open circuit. So it passes all of the voltage at low frequencies, and it's going to attenuate all of the voltage at high frequencies because it starts looking more and more like a short. Well, this inductor right here behaves in the exact opposite way, right? So at very low frequencies, it looks like a short circuit. And at very high frequencies, it looks like an open circuit. So at low frequencies, we have our voltage drop applied directly across this resistor. So our output is exactly the same as our input. At very high frequencies, this guy looks like an open circuit, and none of our input signal actually makes it across to the resistor because there's no current carrying path for it to happen. So that's why this particular combination of inductor in series with resistor, and then we take the voltage drop across the resistor, looks like another low pass filter. So let's talk our way through how this guy is going to behave really quickly, right? So at low frequencies, our inductor looks like a short, which means our output voltage is essentially shorted to ground. At high frequencies, our inductor looks like an open circuit, and so essentially no current can flow through that resistor R2, which means that our output voltage is the same as our input voltage. So that means it's a high pass filter. And we can see that really quickly by deleting these guys. And then if I look, nope, don't delete it. Son of a bitch. I'm just going to move this damn thing out of the way as best I can. So if I click here, it is indeed a high pass filter response. We can see that we're attenuating signals over here, and then at about 160 millihertz, we're going to hit 3 dB, and then beyond there, we're passing everything at roughly full strength. And for what it's worth, this guy right here, where we're taking a capacitor in series with a resistor, and then we're only finding the voltage drop across the resistor, has literally the exact same response. Because at low frequencies, none of our input signal makes it to the output because it's all rejected by that capacitor. And at very high frequencies, our capacitor looks like a short. So all of our input signal gets applied across our resistor. Okay. So to wrap things up for today, all I want to do now is literally just draw those circuits and then tell you essentially what the response is going to look like and all of that kind of good stuff, kind of like in a table form, so that you have it before you in case you want it for whatever reason. So let's call this guy right here first order low pass filter version 2. So that was our input voltage in series with an inductor. Sorry. Our output voltage taken across the resistor like so. So our transfer function for this guy comes out looking like R over R plus J omega L, which is a perfectly acceptable way to write it. Breaking it down into its real and imaginary parts, it will look like 1 over omega L over R squared plus 1 minus J omega L over R divided by omega L over R squared plus 1. And for what it's worth, you get to that simply by dividing your original fraction by numerator and denominator by R. Okay. Our amplitude response is going to come out to be one over 1 plus omega L over R squared, like so. Our corner frequency comes out to just be R over L, and our phase response is going to be negative the inverse tangent of omega L over R. Again, not deriving any of this, but the process by which I did the first low pass filter is essentially the exact same process I did for literally all of these things. Okay. Our first order high pass filter, version 1. So this is the one where we're taking the voltage drop across the inductor in the RL circuit, would look something like this. Where our transfer function comes out to be J omega L divided by R plus J omega L. Broken into its real and imaginary parts. This is going to look like omega L quantity squared over R squared plus omega L quantity squared plus J times omega RL over R squared plus omega L squared. Our magnitude response comes out to be omega L divided by R squared plus omega L squared Our corner frequency comes out to be R over L. And our phase response comes out to be the inverse tangent of R over omega L. And then lastly, we have our high pass filter using a capacitor. So in this case, we're taking the voltage drop across our resistor. As an inductor. We're here, our transfer function comes out to be J omega RC over 1 plus J omega RC, which can be broken into its real and imaginary parts as omega RC squared over 1 plus omega RC squared plus J omega RC over 1 plus omega RC squared. The magnitude response is omega RC over the square root of 1 plus omega RC squared. Our corner frequency is just 1 over RC. And our phase response, theta as a function of J omega, comes out to be the inverse tangent of 1 over omega RC. All right, we're wrapping up 4-ish minutes early. So anybody have any questions, comments, or concerns? If not, we will talk about second order filters on Wednesday. Josh, what was your question?
It was, when you were showing it in LT Spice, like, it may be something simple, but just like, I guess, why did the phase not change? Or just should it not change? It's just gonna be like a fixed value.
So let me pull back up that LT Spice because I genuinely don't know what you mean by the phase.
The dotted line.
Yeah. So for, let's see, so for V out 2, so this is a high pass filter.
Right.
We can see, it's actually,
I didn't know if it was like something that should change, like per filter, or if it's, the reason why it's like that is because of the specific filter. Or if it's just.
so the phase for the high pass filter and the phase for the low pass filter are different things. So let me show that to you real quick, like, okay? So what I'm going to do is I'm going to delete this and this, right click and add a plot plane. And on this topmost plot plane, let's put our simple low pass filter. And for our right hand plot plane, let's do our simple high pass filter. Shit, I forgot to click the other one. I wish I had brought my mouse. Clicking into that one, now clicking this signal. So these frequency responses look
similar. But they are actually very different, okay? So what I mean by that specifically is if we look at the phase response of our low pass filter, which is the out one, our phase angle starts at 0 degrees and then it gradually transitions to negative 90 degrees. For what it's worth, it's going to hit exactly negative 45 degrees at our corner frequency. That's another way for us to identify where our corner frequency is. Whenever our phase hits negative 45 degrees for one pole or negative 90 for two poles, et cetera, okay? Down here, our phase is starting off at 90 degrees out of phase, and then it's gradually transitioning down to 0. So the shape of these curves is the same, but this guy starts at 0 and goes to minus 90. This guy starts at 90 and goes to 0.
I just didn't see the.
Yeah, absolutely.